Am I?
At some point, we're live now.
Okay.
The video has come in. We can just stop at some point to make sure you can hear you on board. So whenever you want to unmute.
It's already on mute.
Okay, can you change the sound and mode?
Am I audible? Can you hear me? Good.
I just really understand the differences between crossbar and
like not that bad, but like
It's okay. Yeah, we don't have probably wireless issue with this one. So.
Yeah, that's very nice. So, and they are currently this is on that and then you what other APIs takes care of. You require more hardware.
Okay, let's get started. Good afternoon, everyone. Welcome to another lecture in Fundamentals of Computer Architecture, Lecture 8. I'm Mohammed. I'm an official co-instructor of this course. And today we're going to talk about GPU architectures. We're going to build on a lot on the topics that we covered during Premiere last week on SIMD, SIMD execution, use paradigm, vector processor and array processor, to be quite powerful in this domain. And I have worked a lot on GPU architectures. It's actually quite close to my heart. My PhD thesis is all about GPU architecture, how to optimize energy efficiency and register file. So it's actually, I'm quite excited that I'm teaching my first lecture in FOCA and also it's GPU architectures. Okay, so we have covered a lot of different execution paradigm in this course. I think we haven't covered yet systolic arrays. Probably we will cover it later in later lectures. But last week we started talking about SIMD processing, vector and array. And today we're going to talk about graphics processing unit or GPUs. But before that, these are also some readings for today lecture this week. But I want to basically to jog your memory. I'm gonna quickly go over some of the slides, some of the important concepts that we covered last week to remind you. So remember that SIMD processing is all about to exploit data parallelism that we have in many important applications, which is also called as regular parallelism. When you think about doing operations on vectors, on arrays, like you want to add two vectors, base element wise. So that's the application that you can benefit from SIMD. So you remember that we covered this Flynn taxonomy of computers, and we saw that SIMD is single instruction, multiple data, is a great way to exploit data level parallelism. And array processors and vector processors are a very good example of how we can implement them SIMD in our hardwares. And SIMD is very efficient because you can amortize the fetch over billions of operands. So you fetch one instruction, you decode that instruction, and then you're going to execute that instructions on many, many operands. And that's you can provide a lot of efficiency and parallelism. So we talk a lot about array processor and vector processor. In array processor, we know that we have multiple processing elements, and each of them are quite heavy. I mean, they can do a lot of operations. And essentially, in your vector, you can assign your instructions to each of these processing elements. So in each time, because you can do load operations in different places on different processing elements. And then on the next cycle, you can go to another instruction and so on and so forth. So you have basically same operation at same time and like this. And then you have also different operation at the same space because your processing elements are powerful and they can do a lot of operations. On the other hand, we have also vector processors that in order to reduce also the cost, that's one of the good way to do it. So you have different processing functional units that they are specified for doing some operations like load, addition, multiplication, and store. And then you do pipeline. So on this load operation, you can pipeline load instructions across different array elements in consecutive time. And so when you have your pipeline full, you can see that you're basically executing different operations at the same time. And that provides you parallelism and performance. So that's the difference between array and vector processor. And in order to make them effective, you really need to feed the pipeline with the data. So that's why these array processors and vector processors, they're relying on high parallel memory and memory banking. And so, and basically you need quite bandwidth in order to access your memory. And that's not only your off-chip memory access, it also needs, you also need high bandwidth for your register file when you want to access a register and bring them to your pipeline. So we talk about this memory banking, and we're going to also learn a lot about memory system later. You're going to see that this is one of the most important parts of our memory system, basically our computer system nowadays. And this is a very good example how we can combine this paradigm, how we can combine array processor and vector processor. Here we have an example for vector processor that you have a processing element, and then you have basically different elements of your arrays, and you're feeding them to your pipeline. But then what you can do is you can multiply, and you have different of these processing elements, different instances of them, and have it in the space. And then you can basically categorize your data and map them elements that they are corresponding to each of these processing elements. And with that, you can have kind of array processor, and each of them is a vector processor. And with that, you can combine these two paradigms nicely together. I'm actually skipping these slides relatively quickly because they are kind of reminders for you. And yeah, and actually you're gonna see all these slides today again. In fact, this one we're gonna see a lot when we want to use GPUs and say how GPU are running these operations. So I'm not gonna repeat that again. And we talked about a lot about advantages of these architectures, SIMD, array processor, and vector processor, but it's also good to know what are the issues. And the main problem is that these architectures, they work only in the sense of to be effective. because these processors are also general purpose. So you can run any application on if you want, but if you want to have good speed up and good efficiency, you really need to have an application that have quite good data parallelism. Like for example, matrix multiplication. If that they can provide very good performance for you, but if not, basically your performance will be limited, meaning that, for example, most of the time you're instead of having a vector with a lot of active lanes and active elements, you're doing operation only on one element, which is not really useful for such architecture. So basically, they are very inefficient if parallelism is irregular. Like for example, very good example of that is in pointer chaining, for example, in linked list when you are searching for a key. And you can actually read this note from Fisher from this VLIW paper. And also we say that if the application is regular, then actually we can automate this data level parallelism, and basically SIMD instruction generation can be automated. And we work on this example that you can see that from this code, everything is so simple. So you can easily do SIMD instruction because you have a for loop, and then you want to do addition across these two vectors. And so that's perfectly parallelizable, essentially. Okay, and yeah, we talked about vector and SIMD machines, that they are good at exploiting regular data parallelism, but also we discussed about performance improvement limited by vectorizability and of the code. And we brought up again this Amdahl's law, which in the end, your performance might be limited by the serial portion of your application. We're gonna actually learn a lot today about many existing ISA that they include SIMD operation. That's actually one of the things that I'm gonna cover in more detail. And this is for our Amdahl law, just as a reminder. So we should not really forget Amdahl law when we are designing architectures and when we are programming, essentially. Okay, so let's see now how are these SIMD operations are happening in modern ISAs. So the ISAs that we had in the past, they were handling basically scalar operations. And during the basic decades, like 1980s or so, people realized that we do need these kind of SIMD instructions in order to, for example, accelerate applications like graphics. And then the idea was that, for example, using our current scalar operations, like you already have, for example, instruction that you can do addition of two, for example, 32-bit register. So you add these two 32-bit register and then store the result on the third register, for example. Then they just come up with this nice idea that they can chunk this array. For example, here they are chunking this this register to 4 elements. Now we can actually call it as vector register because this you can consider that you have 4 elements in your register, and then you just do addition. And the only thing you really need to do is you don't propagate the carry from the first element to the second element. If you don't do that, then basically you have a element-wise addition of these two arrays, right? So you can easily extend the ISA that you have in order to support vector operations. And people have been also doing that in for some other operations, like, I don't know if you know, for example, BCD, when you want to binary decimal code. When you, for example, for decimal code, like 89, the number 89, you don't binary code it. You just encode the first 8 to 4-bit and the 9 also in 4-bit. And when you want to do operations on these encoding, you do need such also support. You don't need to necessarily propagate carries, for example, or you may need to propagate carry in a different way. So people have been doing that a lot. And I think that kind of experience also help people to build quickly on such stuff as well. Okay, so this is an example I set for 8-bit numbers. Yeah, and I said that basically we need to modify ALU, but that's not very big modification for sure. So Intel actually was one of the, I guess, the first one that started doing that, and they described this ISA extension. They call it MMX, multimedia extension, if I'm not mistaken. Later on, they also changed the name for many reasons, for marketing reasons as well. But this is actually one of the very interesting extension that they have done it. So in their normal scalar operation, they have registers of 64 bits. So you can do addition, multiplication, or such operations on a scalar when you have 64 bits. But you have this possibility that you chunk these 64 bits into 2 chunks, and then you have a word of 32 bits. And or in other words, you can say that now I have a vector register that have only 2 elements. You can even go further. You can chunk it to 4, or you can chunk it to 8. And in this, actually having 8 bits chunks are actually quite good when you're doing image processing, for example, because pixels are usually 8 bits, for example, and then you can use it nicely in order to do graphics operations. Interestingly, they didn't need vector length register. So different vector lengths, or how do you chunk it, is actually specified by the opcode, by the opcode of that instructions. So basically, opcode determines data type, and as I said, you could have 8-bit bytes, 4, and so on and so forth. And when you are accessing memory, stride is always equal to 1. So if you remember from our last lecture, when you want to fetch when you want to load, you need to provide effective address, right? Effective address for each load operation. So in a vector, you also need to consider your stride. So a stride is set to 1 here, so you cannot change the stride. Yes.
But is the stride because of the 8 bits within that one chunk, or is it because of the next chunk next to it?
No, it's not related to that. So you have a load. Imagine that you have a load operation here, and so that load operation. So you calculate your effective address for this one, and then you want to go for the next one. You just increment the address by 1, for example. Okay, and you can learn more about this ISA from this paper. So they actually also, yeah, okay. Yeah, here is an example of this ISA that they call it this packed compare greater than word. This is the way of showing this instruction. You can see that the pack compare equal or greater than. And so in this example, we are showing that, for example, you are having 4 16 bits of elements, and then you can do this operation. Another interesting support was, for example, supporting multiply addition, which is quite useful when you want to do dot product. So in dot product, you need to multiply, and then you need to do reduction sum. And in this ISA, they actually provided this support that, for example, here you can do multiplication over these 2 vector register. And then you have the multiplication of element wise, and then you have reduction sum in 2 basically position here. Yeah. And you can see how we can use that for example, doing basically dot product. If you're interested, you can check more, but that's not really magic. It's easy once you know the instruction and once how they map it. Here is also an interesting example that they provided. Unfortunately, they didn't provide the picture, colorful. So we just give you some color here. So there is a lady here, and then the background here is blue. And we have another image, which is a bluesome background. And essentially, you want to put this background for that lady, so such that that lady has a better background. So if you want to write it in a C, in a scalar way, you can just say that you have these 4, and then you check the pixel of each pixel of this image, if it's blue or not. If it's blue, you just replace it with this new image. And if not, you just replace, you don't do anything. And in the end, you have a picture that, you have a different background. And then you can easily implement this with this MMX. The way you can do it, for example, is that you have a register that you initialize with blue. That's a pixel for blue color, essentially. And then another register that basically MM3 that you load it with your data with your this image X, and then you essentially need to compare if it is equals to blue or not, and then you generate a mask based on that, right? And this mask can be we store it in MMM1 here. So doing that, then you can actually manipulate over this MMM1. So in MMM4, you have this background, basically image, right? Which is Bluestone background. So in MMM4, imagine that you have that Bluestone background. And then in MMM1, you have the mask that you just do AND operation, patch AND operation across these two. And then you got to this basically output, which on the position that you don't want to have that background, we have 0 value. And on the position that you want to have that background, you have basically your Bluestone pixels, right? And you also do for your image as well, for your original image. But for that, you need to basically do the AND operation on negate of your mask. That's why you're doing AND operation negate here. And then as a result of that, you get to the basically another MMM1, which you have your original pixel on those places that you don't want to place with the background, and then 0 on places that you do need background. And then you just need to OR these two together, right? And you get to this MMM4, which is your new picture. And this is the code. You can check it if you are interested with these ISA extension. But of course, your picture might have thousands of pixels, right? And this architecture only provides 8 basically pixels. So you also need to have a loop here, and you go over all the pixels and make sure to finalize your picture. Does it make sense? Good. So yeah, you can read this also note about this Intel Pentium MMX operation that they say that Intel plans to implement MMX technology on future Pentium and Intel architecture processors. And they are still also, they are supporting such extensions. I mean, of course, with different names, which I'm showing here with you. So MMX is the 64-bit MMX register for integer. Later on, they name it SSE, streaming SIMD extensions. And they also provide different generation of SSE. Like the first generation was 128-bit XMM register for integers and single precision floating point. And later on, they also provided double precision floating point and so on and so forth. After that, also they provided AVX, advanced vector extensions, which they provided, for example, 256-bit floating point. And also they provide this support, which is FMA fused multiply add, which is quite important when you want to do dot product. So you do multiply and addition and fuse operation. Basically, you don't need to do it. So there's no intermediate step that you need to store. That's actually a very nice terminology with fusing. When you fuse the two function or two steps together, that means that the output of that step will consume immediately with the next step. So you're fusing these two operations, or you're fusing two kernels together. So if you see some kind of terminology like kernel fusion, for example, in GPUs or in some machine learning, that's actually, you need to remember this kind of idea, that the main idea is that the intermediate result that one step produce, we consume that immediately for the next step. Yes.
This is for storing. This is for saving on consumption of like storage.
For storage, and also not it's not only about for storage space, but also for time, because you need to store and then you need to recall again, like invoke another kernel, for example. So when you fuse, yeah, and you can pipeline it nicely. When you have this fuse operation, you can pipeline the whole thing nicely. Okay, and after that, they also provided MAX, advanced matrix extension, because they wanted to provide a matrix multiplier unit, a tiled matrix multiplier unit. So you can also check if you're interested, but I just wanted to bring overview for you. But basically, SIMD operations are also using a lot in modern machine learning accelerators. I'm not going to detail of that. There are many, many different accelerators for machine learning that they use SIMD, but I'm going to highlight some of them. This might have you seen already, like in prior lectures, Cerberus, that they come up with this design of wafer scale engine. So these are like, we have different dies, and instead of chopping all these dies and package each of them, they keep them on a wafer, and these dies are interconnect through some switches, and then you can use the whole wafer for your computation. It's actually quite exciting. I'm going to show you this picture. So this is your chip in Cerebras that you need, for sure, you need a lot of power to power up this. But it's also quite efficient in the sense that you lose a lot of power and efficiency when you want to go outside the chip because of packaging overhead. But here, because dies are actually connected with thinner metals and thinner connections, you consume less power and also you're much faster in your data movement. Yes. Some people are saying that, yeah. It's not hard to imagine, right? Yeah, yeah. I mean, if you're actually, I'm gonna show you a slide that we had a Safari live seminar that we invited some people from Cerebras that they gave a talk. So you can also watch that if you're interested. But of course, power up is cheap and also cooling down is actually so hard. And the thing is that so the thing is that this chip is so powerful. So if you want to, for example, do computation comparable to what you can do here with, for example, with GPUs and some other, you also need to use a lot of GPUs. And for those also a lot of GPU, you need to also spend a lot of power. But the main difference is that that might be a bit more distributed. So maybe cooling down is easier, but here you really need to have a very sophisticated process. Yes.
So here we have everything on one wafer, but if we have manufacturing defects, we lose a lot of our surface area.
That's true.
Because we have to deactivate a lot of stuff. Wouldn't it be better if you do something similar to what Apple does with connecting chiplets and then package the whole thing?
So the thing is that what Apple is doing, which is also is a known technique that other companies are doing. But in that, we are much limited in the number of dies that you can pack them together and interconnect together. So the idea about this wafer scale is that you can connect several dies together, many dies actually. So I think these are not really comparable to each other. But as what you clearly mentioned, that's one of the issues, that some of these dies may not work at all because of the yield and many other issues. One exciting thing about this architecture is that you can actually reconfigure switches nicely and then just bypass faulty nodes. But then, of course, the power of your wafer is reduced when you don't have many of them active, of course. Yeah. But why I'm showing this? Because this architecture is actually kind of considered as MIMD, which is multiple instruction, multiple data, because each tile and each die is actually doing computation on different layers of neural network. But underneath, each of these elements are actually SIMD engine. So you have a MIMD machine, which is distributed memory, and you are connecting them with a 2D mesh interconnection fabric. But essentially, you have a MIMD machine with SIMD processor. So each of these small dies, they are actually SIMD machines, which is quite exciting. So if you want to learn more, I would suggest you watch this Safari Live seminar. It happened some time ago in 2022. Okay. Any question? So now I'm gonna jump to graphics processing unit, and we're gonna see a lot that how GPUs combine array processor and vector processor, and what the nice trick that they made in order to make their programming much easier. So, but I want to first start with some motivational slides. So this is kind of evolution of recent GPUs. And we are showing here actually from Volta, which is the architecture released in 2017 or so, if I'm not mistaken, through Blackwell, which is the most recent architecture of NVIDIA, which I guess introduced around this time, actually last year, in March or so, I guess. And so these GPUs, as you can see, they are integrating more and more transistors. So like in this Blackwell, we have more than 200 billion transistors, and they are getting beefier and also bigger and a lot more powerful in doing computation. But the problem is that for today's applications that one GPU is not enough because for two main reasons. One of them is that you need much more memory capacity, which one GPU cannot provide that. So people combine several GPUs together to provide that memory capacity that they really need. And at the same time, when you provide that memory capacity, you also need to provide the computation power for that. So as a result of that, people, Nvidia also and other industry, they try to combine GPUs and together and interconnect them nicely to provide performance. So they actually improve a lot on also the way that they can connect GPUs. This is the architecture they provided in Ampere that they use NVLink generation 3, and then in Hooper and then Blackwell. So basically, you can see that you don't need to know a lot, but what they are showing here is that their interconnection is less and provides better bandwidth as they grow. And this is what I already said, like we need basically multi-GPU system to interfere at a scale. And also different interconnection network. But the thing is that fundamentally, all GPUs are the same. And I want to now to go into the fundamental way. So GPUs are SIMD engine underneath. The instruction pipeline operates like a SIMD pipeline, like array processor and vector processor. But the main difference is that the programming is done using threads, not SIMD instructions. And that makes a lot of difference here for us. So to understand this, we will check our parallelizable code example that we have seen also before. But before that, I like to distinguish a bit between programming model, which is at the software level, and also versus execution model, which is happening at the hardware. So programming model refers to how the programmer expresses the code, like sequential following von Neumann model, data parallel using SIMD or data flow or multi-threaded MIMD, SPIMD, and so on and so forth. So that's a programming model that you might have used. How many of you have already programmed parallel code? Yeah, so that's a kind of programming model that you can use when you want to parallelize your code. But execution model refers to how the hardware executes the code underneath. It can be, for example, out-of-order execution, which we have seen in last lectures, vector processor, array processor, data flow processor, multiprocessor, multi-threaded processor, and so on and so forth. So execution model can be very different from the program model. For example, you can have a von Neumann model that you write your program following von Neumann model, completely sequential, but then you can run it on an out-of-order processor, which underneath this code is actually executing out of order. You still need to commit and retire instruction in the programming order, but that provides a lot of parallelism for you. Or for example, a SPMD model, which is single program, multiple data, meaning that you run one single program on different data elements. For example, your program is addition of two arrays, for example. So that's your program. And then you run this program on multiple billions of data elements. So that's the paradigm, we call it SPMD, which is more or less actually on the program model. It's not actually executed. SPMD model can be implemented by the SIMD processor, which is exactly what GPU does. So GPU is basically hardware which implements SPMD model on a SIMD hardware. So let's elaborate more with this example. We have this vectorizable loop that we use also in our last slides. So we want to examine 3 programming options to exploit instruction level parallelism that we have here. So by looking at this code, you can see that we have very good parallelism, right? We have several iterations of this loop, and all these iterations are completely independent, right? So we will examine 3 ways. One is a sequential code, SISD. The other one is data parallel, for example, using SIMD, and then multi-threaded, like MIMD or SPMD. So if you start with the sequential code, you can execute this on a pipeline processor, on out-of-order execution processor, which independent instruction can be executed when ready. And different iterations are present in the instruction window and can execute in parallel in multiple functional units. Because all these iterations are completely independent, and it's actually one of the very good examples that your out-of-order processor can easily provide parallels for you. So basically, this loop is dynamically unrolled by the hardware. So that's once you use out of order execution. In that instruction window, you're fetching your fetching instruction, you're decoding, and all you have a lot of these operations of addition, right? So all these addition instructions are coming, load and addition, you have in your instruction window, and you can just or in the sense that you're kind of unrolling this loop, in your hardware. So you can also use superscalar or VLIW, for example, for running this application. So you can see that I'm saying all these examples to justify the difference between programming model and execution model, essentially. Another way is that, so we have a realization that each iteration is independent. So we can actually have a programmer or compiler to generate SIMD instruction for us. So because it's actually automated, it's quite easy to vectorize it. And then you can basically execute the same instruction from all iterations across different data using SIMD programming, essentially. So I'm skipping because it's not, you're already aware of all this. And this can be executed by a SIMD processor, for example, like vector and array. Another way would be, I realize that each iteration is independent. So I'm going to assign each iteration to a thread. So programmer compiler generates a thread to execute each iteration. And each thread does the same thing, but on different data. This can be executed on a MIMD machine. So this particular model is also called SPMD. So because your thread is actually the whole program. You don't have a, basically in some kind of model, for example, you have a program and then you make some threads, they do something, and some of these threads are also doing something differently. They don't do the same thing. And then you merge them and then you continue. So that's a general multi-threaded, for example, paradigm. But here, all of your threads are doing exactly the same thing, addition operation, right? Load and addition. That's why we call it single program, multiple data. And this can be executed on a SIMD machine, which I don't want to confuse more, but this is also called SIMT machine. This is terminology that NVIDIA use, single instruction, multiple thread. And SIMT is actually a quite nice terminology, in my opinion, that NVIDIA uses. Sorry?
They're the exact same, just terminology.
Yeah, just like it actually reflects to when you do SPMD on a SIMD machine, you can call it SIMT. So basically, SIMT is a terminology that specifies kind of programming model and execution model together. So that's why it's actually quite nice to have this terminology. Okay, so a GPU is a SIMD or SIMT machine, except it's not programmed using SIMD instructions. It's programmed using threads, a SPMD program model, and each thread executes the same code but operates a different piece of data. So each thread has its own also context, can be treated, restarted, executed independently. So when you write a GPU code, you actually think that you're writing a scalar code because you're writing a code for a thread. And you don't need to worry about many different threads that you have because all of them are going to be the same. In some part of your code, you might also break the rule a bit, because you cannot do, for example, you want to do reduction, sum, and you have a lot of threads, but then at some point, your number of threads is reducing as you want to reduce do reduction sum. So then you need to have some threads that you do some operation and some threads that they are not doing operation. So, but overall, these threads are basically execute the same code. And a set of threads executing the same instruction. So you have all threads have the same code. Like you have one kernel that you're gonna invoke or launch it for all threads. But then in that kernel code, there are many instructions, right? So there are, given a time, there are some threads that they are running exactly the same instruction because they are exactly at the same program counter, for example. So those threads are dynamically grouped into a warp or wavefront. Warp is a terminology from NVIDIA, wavefront is for AMD by hardware. So that's exactly like how hardware is making SIMD operation dynamically for you. So you're writing a code for threads, and then dynamically in the hardware is mapping, grouping these threads together to form a warp. And that warp is actually essentially SIMD operation that's happening. Make sense? Yes.
So this hardware grouping, is this complicated?
So it can be. If you want to be super flexible and efficient, it can be very complicated, and people have looked into it a lot in the research. But industry, in Nvidia and AMD, they try to be not that much complicated. So I'm gonna show some slides related to that. So they made some trade-off to make it simple and it's still effective. Very good question. Any other question? Yes.
So multiple warps doing different slightly different instructions is often considered as one big
Yes.
ED then?
Yeah.
Okay.
Yeah, so our GPU kernel has, I'm going to show it later, but we have many threads that we group them in at the software layer, we group them in a block. So we call it block of threads. And the programmer just assign block of threads to the GPU. And then hardware tries to make these warps actually out of those blocks. So programming does not need to deal with warp at all. But in order to do a good, to program it nicely and more efficiently, actually programming needs to be aware of the warps, because that can provide much better performance. That's why actually programming GPU is easy if you want just to implement and get some speed up. But if you want to implement and get the very good speed up, and I'm not going to say the best speed up because that's a very strong word, but as much as you want to improve your code, you really need to be more expert and think deeply, you know, and also at some point you need to come up with better algorithm to parallelize your code. Okay, so going back to our example, we have this SPMD on SIMT machine, and the warp is a set of threads that execute the same instruction at the same, or meaning that the same program counter. So in this example, for example, we can have warp 0 at PC X, and then that warp can go to the next PC, to the next PC, and the next PC. And then you can have many of these warps that they are doing your operation for you. Any question? Good. Okay, so we already know that. And so let's also a bit compare what is a SIMD versus SIMT execution model. So SIMD, a single sequential instruction stream, sorry, a single sequential instruction stream of SIMD instructions. So in SIMD operation, you have one single instruction and you are streaming that instruction over many data elements. And each instruction specifies multiple data inputs. For example, you have vector load, vector addition, vector store, and then you also need to specify vector lengths. Or somehow specify with your opcode essentially. So, but basically programmer needs to deal with all of these. Programmer or compiler need to deal, but not many applications are easily vectorizable. So sometimes programmer really, sometimes they need to do a lot of effort to vectorize their code. But in SIMT, we have multiple instruction streams of scalar instructions. So basically then you have just a scalar operation like load, addition, store, and you just need to specify the number of threads that you need. So when you're programming, you just program for one thread. You're basically writing a scalar code, and that makes the whole easy. There are two major SIMT advantages, which we're gonna cover it actually today. First one is that we can treat each thread separately, meaning that it can execute, we can execute each thread independently on any type of scalar pipeline. For example, it can be, so it can be MIMD processing. So really each thread can be separate. Even though in order to be efficient and provide very good performance, you want to have as many as possible threads that they are doing the same thing, exactly the same thing, such that you can have your pipe, your warp full active, and then you provide a lot of performance. But it's also quite easy, and you can do it. And it's also, I would say, essential for some application at some point that you need to treat each thread separately. That basically not all threads needs to run together at the same time, and also not all threads needs to run the exact same code at the same time. So, and that provides a lot of efficiency and I would say programming ease for you. And another important SIMT advantage is that we can group threads into warps flexibly. We're gonna see a lot about that later also. But let's first start with the first one. So the thing is that the idea of GPUs, the way that they treat warps is actually, you have seen this idea before. Fine-grained multithreading, right? I think in lecture 6C, we covered fine-grained multithreading of warps. Not warps, but fine-grained multithreading, essentially. So the main idea of fine-grained multithreading is that whenever I have a stall in my pipeline, I don't try to eliminate that stall. I just try to do something else, you know. And you have a lot of threads, and you can quickly context switch across these threads. And in order to have fast context switching, you need to have context of all threads on chip available. So that's why in fine-grained multithreading, we usually need a big register file, because you need to have registers for all threads available, such that you can quickly switch between them. GPUs are essentially doing the same. So they have many warps available. And whenever a warp encounters, for example, a load stall, you know, waiting for memory access, you just switch to another warp. And then with that, you can keep your pipeline full without stalling. That might not work all the time, because as you can imagine, we might not have enough number of eligible warps. We might, have quite long latency in access memory. And that's why also NVIDIA does not only, rely on this fine-grained multithreading or multithreading of warps. They also added caches. They try to, for example, have a deeper cache hierarchy in order to reduce memory access latency. But the main focus is actually fixing stalls by using fine-grained multithreading. But for example, in Fermi architecture that they announced in 2009, I guess, they added, for example, L2 cache. They didn't have L2 cache before. In 2009, they realized that they do need L2 cache. And then as of now, they actually keep L2 cache and they make it bigger and bigger. Like I think in the recent architecture, they have something 60 megabyte of L2 cache, for example. Okay. So now let's see what is a fine-grained multithreading warps with better example. Like assume a warp consists of 32 threads. If you have 32K iterations, then meaning that you need 1,000 warps, for example, where you're running your application. Warps can be interleaved on the same pipeline, which is fine-grained multithreading of warps. So here, as an example, warp 0 can be at PC X, and then warp 1 can be sometime later, can be at this PC, and warp 20 can be at PC X plus 2, for example, sometimes. So you are basically running them in different way. And the thing is that all threads in the warp are independent of each other. I mean, that's what we really want. Sometimes that's not the case. And that's why NVIDIA also tries to add some instructions that threads in the warp can communicate each other. They added instruction like shuffle exchange that threads in the warp can communicate. But the main way, the main idea is that we want all threads in the warp to be completely independent. And warps also, we want them to be completely independent such that we can run them in any order. Let me, yeah.
So if warp 2 encounters a load problem, so large latency, then immediately context switches to warp 1 and continues with addition.
Yeah, so yeah, but that's not necessarily warp. I mean, we have a warp scheduler.
Yeah,
in this example, yeah.
Like
Yeah, exactly. Okay. Yeah. Yes.
Doesn't it happen very fast that warps fall apart?
Yes, actually, because of memory access.
And what about greediness?
What about?
Greedy, like a warp. So warp 2 context switches to warp 1.
Yes.
Warp 1 then hogs the GPU for as long as it requires.
Mm-hmm.
It doesn't ever have a problem. Then warp 2 suffocates now. Or do you have? Like,
oh, okay. Oh, I see. So you're thinking about fairness of our scheduling.
Yes.
That's true, actually. So in people that they are doing research on warp scheduling, they try to make it fair and also high performance, because sometimes when you are acting too greedy, you try to run instruction from one warp as much as possible, then you actually get to very bad situations.
So it's similar to CPU where they have like a fairness schedule.
Yeah, exactly. So there are a lot of research going on in that also, in warp schedule. Yeah. So this is just a reminder for you about fine-grained multithreading, and this is the lecture we had actually in FOCA. And if you are interested, you can also check this one from our DDCA course in 2022. Okay, let's have a break, but not for the whole time. Let's be back at 3:10 for 9 minutes break. Thank you. Yeah, let's see. Yeah. Can you say something? Can you hear me?
Yes, again.
Can you hear me?
Ah, yes, that's just okay.
Good. Okay. I think it's not 3:10. It's almost. So let's get it started again. Okay, we were discussing about warps. Warp is set of threads that execute the same instruction. We can have many warps, and then we need to schedule across them. And basically, you run your warp on a SIMD pipeline, and in that you have a scalar thread execution essentially. So, the backend of your execution in GPU is actually scalar in a vector. So you have a scalar functional unit, which it can be also pipeline. So that's why we have it like a vector processor. But then we have several of them, which is similar to array processor. So that's why how we combine these two together. It's a high-level view of GPU. It's actually quite old, this version, but a lot of fundamentals are still the same. You have several cores. They call it shader core, which is actually coming from graphics terminology. Those cores that they were doing shading for graphics applications. This is actually part of a story that I didn't cover much today, but NVIDIA, like people in the past, we didn't have this possibility to use GPUs for running, our high performance computing applications. Around the years of 2000 or so, there were some intelligent people that they realized that, okay, if they just make a nice analogy between their application and also graphics application, they can use GPU for them. And also some researcher in the GPU in NVIDIA, apparently they were also following the same thing. And, but then basically NVIDIA also realized that, okay, that's a very cool idea. And then try to extend their ISA and also this, they provided this CUDA support such that they make it more automated. So nowadays that we are working on GPUs, we don't need to deal with graphics pipeline essentially. But in the past, like in 2001 or 2, there are some papers that the people actually use graphics library in order to do, for example, matrix operation. Okay, so this shader core interconnection network, and then you have memory controllers and access to your off-chip memory. And in a shader core, we have basically some, the front end, which is the program counter, mask, caches, your decoding to decode instruction, and your SIMD execution model. We're going to see more about that. And I discussed already about latency hiding, which is happening in warp level fine-grained multithreading, which NVIDIA actually relies on that a lot. GPUs, essentially, they rely on that a lot. Okay. And in order to accelerate this, make it possible, so you really need to have register values of all threads available on chip in the register file. And that's why GPU register files are actually very big. Like, for example, we have 256 kilobytes of register file per GPU core, which is 64K 32-bit register per core. And during my PhD, actually, I realized that even that is not enough. And I work a lot to design a register file which is 8 times larger, like 2 megabytes per GPU. You can check that paper in ASPLOS 2018 LTRF. Okay, we already shown this picture, and now we want to see how does it look like when you have warp. So essentially, you have your warp and different threads. I'm going to show here, actually, it's better. Yeah. So this is your recall for you, but then you can have a warp 0 that doing load operation, and at some point another warp 1, for example, doing accessing your multiply unit in your vector processor unit, and then warp 2 can be in addition unit, and then warp 3, for example, in load unit, and warp 4, warp 5. So this is how you can, for example, do interleave these warps, and they are doing different operations. And here you can see that if your SIMD engine is, for example, 8 lanes wide. Your warp is 32 bits, not 32 bits, like 32 threads. You assign 8 threads and then you run them in parallel in that processing element, like in 8 processing elements, but then you need to pipeline them, the rest of it. So you need to run 4 iterations of one 32-bit warp, 32 thread warp in order to finish, for example, the execution of warp 0. So that's the part that you are combining array processor and vector processor together. Does it make sense?
So each one of these dots and triangles and everything, these are all a single
Thread.
processor.
Single thread, no processor.
Single thread.
Yeah.
These are all ran on individual processors.
Yeah, but you don't have enough number of processors.
Sorry?
You don't have as many as threads number of processors in your GPU. So you need to interleave them and run them concurrently.
Yes, these are all like pipelines.
Yes, yeah.
Oh,
Not all of them, like you can see that like 8 threads are running in parallel completely because this is the time, right? So all of these 8 threads are running in parallel because you have 8 parallel engines. But then after that, you need to pipeline basically, next cycle. Make sense? Good. Okay, and for memory access, same instruction in different threads uses the thread ID to index and access different data elements. For example, here you have, consider you have the 2 arrays that each of them is 16 elements, and you want to run them in on 4 warps, and each warp has 4 threads, for example. So you have warp 0 to warp 3, and then essentially each of these warps has a thread ID. So in warp 0, we have thread ID 0, 1, 2, and 3. And in warp 1 also, we have thread ID 0, 1, 2, 3. And then if you combine the thread ID with your warp ID, then you can get to the unique ID. And based on that ID, you can actually access your memory. And that's the way that your address calculation in the hardware is quite easy. And that's why actually it's actually coming from SIMD. So in SIMD also, you don't need to pay a lot when you want to calculate your next address of the memory. So most of the time we are calculating address with the stride easily. So here also you can see that it's just using thread ID. Okay, so for maximum performance, memory should provide enough bandwidth, as we know also for SIMD. And that's why actually GPUs are integrating high bandwidth memory nowadays. HBM2 and now HBM3, for example, that for example, I think in in Blackwell architecture, they have 8 terabyte per second memory bandwidths per GPU core. And again, that's not only also off-chip memory or the GPU memory, is also the register file should be also high bandwidths. So because of the register file in GPUs are actually quite banked. There are several register banks, and there are multiple operand collectors that they are fetching register values, preparing them in the operand collectors, and then to feed to the pipeline. So we need high bandwidth everywhere in the GPU, because if you don't have that bandwidth, fine-grained multithreading is not going to work well for you. Okay. So warps, as I said, they are not exposed to the GPU programmer. When you want to run a GPU program, you actually have a mixture of CPU threads and GPU kernels. The parts of your program which is sequentially or modestly parallel section, you write them for CPU, and the rest massively parallel sections on GPU, like blocks of threads. So for example, in this show that you can have a serial code that's run on a CPU host, and then you have a parallel kernel device that this is the notation for NVIDIA, for example, in CUDA. When you want to invoke a kernel, you just mention the name of the kernel and then specify the number of blocks and the number of threads per block, if I'm not mistaken. And then some arguments that basically you need to pass through that block. And this is going to look like something like this. Each of these is a block. And we have many of these blocks. And another terminology is that we call it a grid. And when it's done, basically we do another, for example, serial code. And then we can invoke another kernel and so on. So yes.
And scheduling and such is done with serial CPU.
Scheduling of
organization of all the data, threads and such is all like the CPU part.
Yeah, you mean, okay.
Like to figure out which threads require what and how many threads affect my.
No, this one is actually should be calculated by the program.
Oh, okay.
So program needs to realize how many threads, how many blocks, for example, you need.
Like
but these are GPU threads. These are not CPU threads.
Yeah.
So in your GPU program, you have a actually CPU code, which actually start with int main, for example, you know, like as you write. But then in that code, you invoke a kernel, a GPU kernel. And for that, you need to first allocate some memory in your GPU memory device. And then you need to move data from CPU memory to GPU memory and then invoke the kernel. Okay. But that invoke can be blocking or can be non-blocking as well. So sometimes you can invoke a kernel and then CPU can keep going, because you are not dependent on that. You can do, but at some point you are dependent on the result, then you can add some barriers that you wait, and then you do. Yeah, for example. So sample, for example, GPU code. This is your CPU code, for example, and this is your CUDA code, which actually quite simplified here. But essentially, you need to calculate thread ID, which you can calculate your unique thread ID using a block dimension and block ID and thread ID that you have. And using this, you're going to get the unique number of ID. And then you just need to do this operation, like you load from your array A and B based on your thread ID. And then the output array C thread ID would be some of these two. And that's your GPU code. And this is less simplified, which this is your GPU program, which has in the main part, which is the CPU part that needs to be run on CPU. And this is the part that basically is your kernel. Here you are defining some, your basically block and grid of threads. And then you need to call this GPU program, add the matrix, and then you mention this grid and also the dimension of your block. And these are the arguments that you send to your GPU program. Of course, I'm not covering detail of programming. So if you want to, you know, get your hands a bit dirty with GPU programming, I would recommend you watching this lecture. And we also had a PNS course in the past on heterogeneous system course that we provide a lot about how to do GPU programming. One of my former colleagues, Juan, that he's now in Nvidia actually, he delivered nicely this course. And I know many people in all over the world, actually, they are watching these lectures to learn how to start with GPU programming and how to get actually advanced and be expert programmer. So this course is actually quite exciting. I also watched it, to be honest, and I learned a lot. Okay. Yeah, so from blocks to warps, let's see. So this is our SM architecture. This is shown from Fermi architecture in 2009. And we have basically blocks. But the thing is that the programmer sees the blocks and assigns block to the execution. But in the execution, GPUs needs to assign these blocks into warps. So blocks are divided into warps. And so warp size, for example, it can be 32 threads, which is usually more or less the case. There are some GPUs with different number of threads per warp, but 32 is the common number. And the different warps are belonging to different blocks. And that's actually very important, when which you should know. The hardware should make sure that basically do not do not share information across these blocks. So basically, when the hardware is grouping threads to make a warp, those threads should belong to the same block. So for example, the hardware should not select a thread from block 1 and group it with threads in block 0 to make an instruction, to make a warp, because that can violate some programming model.
So like there are two different programs?
No. There might be actually the same program. But the thing is that there are some, so what I'm also saying is that it's also very dependent on how we design, you know, and in order to keep things simple, and also some of the, in order to obey some rules that we have at the program model. For example, we have a shared memory in GPUs. which threads that they are in the same block, they can use that shared memory to share data to each other. So if you basically group threads that they are in this different warps, different blocks, then meaning that these can be, I mean, GPU should really understand that these threads, they should not share location in the block because they are from different blocks. So that adds another complexity to the GPU hardware.
Okay, so it's the same program, but they have blocks which are independent parts of the
Exactly.
same program.
Yeah.
And they shouldn't interleave.
Exactly. For a long time, actually, GPU was not supporting synchronization a lot across blocks. So when programmer wanted to communicate across blocks, most of the time they had to do coarse grain synchronization, like shut the kernel or finish the kernel, then make them synchronize, and then start another kernel. But now in recent GPUs, they're also providing some support such that blocks can also share information and communicate. Yes?
But why would you make multiple blocks? There isn't the limit of how many threads you can have in one block, right?
There is a limit. There is a limit. There is a limit, and also GPU scheduler assigns several blocks to one SM, which is in each streaming multiprocessor or each core. So if you have only one block, that means that GPU only assign that block to one SM, and the rest of SMs, which can be hundreds, they are useless. But yeah, you're right, actually. I mean, these all these are happening because of some of the decisions that we are making at the hardware and at the program model. So none of them, in my opinion, are really fundamental. Okay. Okay, so I think we already covered this. Traditional SIMD contains a single thread. Again, comparing between warp-based SIMD and traditional SIMD. And ISA contains vector SIMD instruction. But in warp-based SIMD, we consist of multiple scalar threads. And this does not have to be lockstep, meaning that threads that they are in the same warp, they can actually execute independently. They don't need to be completely at the same, they don't need to execute instruction in lockstep manner, meaning that there might be the cases that some threads, for example, they access cache, they access memory, and some threads actually hit in the cache. So they get their data quickly. But some other threads in that warp, they may miss in the cache, and they need to access off-chip memory. So they are experiencing longer latency. If we consider lockstep manner, meaning that warp is going to be stalled until all threads get their data, right? Which usually actually the case for Nvidia GPUs. And I know that in recent version, they also try to, relax this also a little bit. But again, in order to make it simpler, they consider that warps need to be lockstep. But this does not have to be. So in the paradigm, we can actually be more flexible. Okay. And again, you know that software does not need to know vector lengths, and that enables multi-threading and flexible dynamic grouping of threads. And ISA is a scalar. Okay. So SPMD, we already covered it, just a summary, single program, multiple data, and this is a program model rather than a computer organization. And each processing element executes the same procedure except on different data elements. Essentially, multiple instructions streams execute the same program. Okay. Yeah. And this is also, I want to emphasize that each program procedure works on different data and can execute different control flow paths, which at runtime. So threads that they are in the warp, so you can have a control flow graph. Whenever time to time you have some branch instructions that the result of that branch can be taken and not taken, right? And that decision can be related to your thread ID, related to that thread data. So for some of the threads in that warp, you may want to take the taken pass. For some of them, you need to take a not taken pass. And then they diverge. And we're going to see that can actually how we can handle that. Okay. So we kind of finished the first part, but now I want to talk about how we can group threads into warps flexibly. So this is what I was discussing. This control flow graph of your an example application, and you have several threads. But different threads, even though they have the same kernel code, they might take the different passes because they are working on different data. And this can cause basically reduction in your warp efficiency. So a GPU uses SIMD pipeline to save area, as you know. And this can cause branch divergence, which we call it. So you have a warp that all threads are active, and then you reach to the branch instruction, and then some threads wants to take pass A, some of them wants to take pass B. And then this full active warp diverged to two basically less full active or partially active warps. And then after some point, this needs to be reconverged again. So GPU hardware needs to deal with that, which is also not that easy. And that's the fact that GPU hardware handles that makes the programming very, very easy. So otherwise, one of the reasons that SIMD programming is very hard is actually dealing with branches. Because you need to deal with a lot of these masks, as a programmer. But GPU hardware is doing that for you. But of course, if you do it without thinking about the hardware, then your program is going to be super, super slow and inefficient. Because in the end, this is not a good thing. Because you want to have your warp fully active in order to have, quite good parallelism. But now you are not saturating or utilizing your performance as much as you should or you could. Okay. So let's see how we can do this, group threads into warp flexibly. So if we have many threads, we can find individual threads that are at the same PC. Even though these threads might belong to different warps, but as long as they are the same PC, meaning that they are executing the same instruction, this paradigm should let me to, group them to another warp. So I can make a new warp, which is now fully active. So let's see with that can improve SIMD utilization. Let's see with an example. So this technique actually called dynamic warp formation or merging. That essentially you have two, for example, different warps, warp X and warp Y. And then you can say, okay, these two warps are executing the same instruction, but both of them are partially active. So I can combine them and make a new warp, warp Z, with this. And this warp Z, I'm going to run this only at warp X and Y. And this is more active. So you are increasing your SIMD utilization. But in this example, another example at some point, you can see that you couldn't combine them nicely together. Why is that? Because the threads that they were active, some of them, they actually were on the same lane. And in that, you cannot easily combine. Why is that? Because the register file access, as I said, again, in order to be simple, when you want to access register file, your thread ID specify on which register you're getting your data. So when these two are on the same thread ID, you need to at least permute some of them, one of them, right? So then you need to change the ID of one of them. And changing the ID needs a lot of complexity in the hardware, which usually hardware does not support that. Even though this is I'm not sure if it's still active, but people in the past were working a lot on it, how they can, for example, people suggest that we can do rotation. Sometimes by one rotation, you can try to reduce conflicts, or sometimes by doing some tricks. Because so once there are some tricks, then you can make your hardware at least aware of those tricks. But if you want to flexibly just change the thread ID, then that might not really work because the hardware is gonna be super, super complex.
So you have warp X and warp Y on two different processors doing two different things, but then they happen to both have the same PC.
No, they are actually doing the same application.
Oh, sorry, they're in the same block.
Yeah. They are on the same block, actually, yeah.
And then instead of having underutilized two processors, you just merge them into one process.
Yes, not process, to the same warp.
Same warp.
So you make a new warp, and then you combine these two warps together. They call it warp compaction, something like that. So this is like, yes, this is kind of the new warp formation. That's why we call it dynamic warp formation. So you make a new warp compaction, yes. But again, so it is actually considered that these warps are on the same thread block. Yeah. Because if that's not the case, then your program might violate
So the
some.
only real benefit is because of lockstep, because all works have to be in lockstep, right?
The only benefit of what?
So the only benefit of merging the two X and Y's into Z is because of lockstep, because otherwise X would have to wait for its other half.
No, not at all.
No?
No, actually, GPU hardware does not do that. When you have divergence, when divergence happen, GPU consider that you have two warps now,
Yeah.
and then try to execute these two warps separately and then merge them at some point.
Yeah.
But then your graph actually can go to more if and else, you know.
Yeah.
So that's, yeah, exactly. That reconvergence point can be actually quite late. And there are many works they have tried to predict that or reduce that. But here, that's not lockstep actually. Lockstep is coming from the fact that in one warp, the instruction that you are doing, all of them needs to finish that instruction.
Yeah,
but they already finished that branch instruction.
Yeah.
So that's not related to.
Them remerging with something else, so
Yeah,
they
yeah.
can continue that path, and
Yes.
the one that was left over can be remerged with something else. So that
Exactly.
the timing works together.
Exactly. Exactly. Okay. But then if you're lucky and you have another warp, then you can try to, you know, combine this and then make it again more active, and then you can. So this is the idea that has been proposed in this work in 2007. And I already provide you the idea, essentially, that you can try to merge them as much as possible, but you should not forget about this issue. So there are some cases that you cannot do. So there are there are actually, I would say, 3 important constraints when you want to do this. One of that is that these two warps that they want to compact threads together, they should be at the same PC, which makes sense. Another one is that threads should not overlap. Thread ID should not overlap. And the third one is that they should belong to the same thread block, because otherwise this can cause some basically correctness issues. And actually later on, this team actually published paper in 2011 that they tried to tackle the third issue, that they call it thread block compaction technique, that they try to do compaction at the thread block level to make sure that this does not violate that important basically constraint. And here is an example that you can play it maybe at home if you're interested. It's a bit quite slow, but nicely done animation, I guess, here. It's a baseline code that would run like this, but with dynamic var formation, you can. Okay, I should play. So in dynamic var formation, you can actually do, you know, you can combine them and make you, but there are in some cases you are not basically, yeah, here, these two, for example, you can combine them, these two, you can combine them. And then, yeah, in this E and this F, these two E can combine, but then you have an E, which is, you know, you have only one active thread. And basically that would save some cycles for you.
But at E, there was no win, right? There was no winning.
No, yeah, unfortunately. Okay. Yeah, because one of the threads actually conflicts.
So much bigger.
Yeah. Okay, but yeah, this basic, that's exactly what I talk. Can you move any thread flexibly to any lane, you know, to fix this issue that, for example, here you cannot combine them? Well, you can, but that would cause a lot of complexity. So people don't do it. Okay. So analyzing GPUs is very fun. We actually use this concept for exam question a lot. This is an example, and I'm not going to solve you. You can actually check the solution, but you're going to also probably see in August or so some. It's a very nice, you know, exam question for me. I really like this question, to be honest, and I used to design them a lot. I'm not sure this time because hopefully TAs will design it. Okay. Yeah, I don't have much time, but I'm also going to cover a little bit some more concepts very quickly. So we already talked about branch divergence. We also have another issue, which is long latency operations, that we know that fine-grained multithreading in general, you want to use context switching fast context switching in order to hide latency for long latency operations. But that's why our warp scheduler needs to be really intelligent. So because here you have your warp-based fine-grained multithreading. So this work, Professor Mutlu, he has also worked a lot on GPUs. Actually, when I started contacting Professor Mutlu in 2016 or so, to start collaborating with him, back then I was working a lot on GPUs, and I was excited about the works that he has been doing a lot on GPU, and I have read a lot from him. And then I contacted him, and then our collaboration starts. So I have a very good memory actually from this paper actually, because it's one of the paper I read and I enjoyed it a lot. So I'm gonna quickly go over this paper, but not into a lot of detail because we don't have time. But essentially, if you are greedy in your scheduling, that you try to do, try to schedule warps a lot, and they compute a lot of instructions, and then they reach to the long latency instruction all at the same time. Then you don't have to do anything, you're gonna have long stall time. So that's why in this paper, they provided this 2-level round robin scheduling. This work actually has been done with collaboration with Nvidia. I think that they are using this in many GPUs as well, using this two-level round robin. That basically you try to schedule warps and they compute, but then you want to have another group so you schedule a group of warp, they compute, and then you reach to a position that you have long latency operations. But the good thing is that you have still another group that they are in the compute instructions, so you can schedule them. And with that, you can basically reduce the stall time a lot. So this 2-level warp scheduling is very interesting and it's very effective. If you're interested, you can actually check this paper. Also, in this paper, they discuss how we can reduce branch divergence as well by providing this large warp definition. So they define that they can have we have a large warps, then you can large warps, meaning that much larger than 32 threads. Then you can actually flexibly try to make sub warps out of this big large warp and keep your SIMD active and basically do computation. I don't really have time to go into detail of it, but if you're interested, you can check this paper. Okay, question. I'm gonna quickly also show some case studies, some of the GPUs. I'm gonna show a lot of marketing numbers, but I'm not from Nvidia, so. This is one of the GPUs that they provided very long time ago, GeForce GTX 285. And this GPU actually, the numbers that we are seeing here is actually quite like a joke compared to what we have now. But even then, it was actually super powerful. So they had 240 stream processors. NVIDIA also called them CUDA cores, or they also sometimes you can see that as SP. SP is actually acronym for stream processors. And but another terminology is cores, also a streaming multiprocessor or SM. So you should be careful. So like in GPU, we have, for example, in this GPU, we have 30 cores, and in each core we have some amount of stream processor. So basically the amount of SP per core, you need to divide 240 by 30 essentially to calculate. I think it's going to be 8, right? So you have 8 SPs per SM essentially.
And then one block you ban on one stream processor, or
one block or several blocks.
separate blocks on one stream processor.
One is streaming multiple. No.
So one of the cores.
Yeah, one of the cores. Yeah. Okay, and this is the architecture of it, which is actually a bit old in that sense. But again, I mean, today's architecture are also not that different fundamentally. So for example, here we have 64 kilobytes of storage for registers, and we have decode step and also basically functional units for doing SIMD operations like multiply, add, multiply, and so on and so forth. Okay, and warp size is 32, and basically up to 32 warps are interleaved in a fine-grained manner in each SM, meaning that the maximum number of threads that you can have and you can schedule per SM is actually 1,000 in this architecture, because you can have up to 32 warps, and each warp is 32 threads. So that's the maximum number of threads that this architecture had. Later on, actually, more recent architecture, I think we have maximum 2,000 threads. 2 to the power 11 number of threads per SM. Okay, as a structure architecture of the whole, the number of cores that you have and the number of threads. So in total, you can have run 31,000 something around that threads on your GPU. Okay, but basically we are way advanced compared to that architecture in 2009. And you can see that GPUs get beefier and beefier. So you can see that the number of functional units, and here we have gigaflops. And I'm going to show you, for example, Volta architecture in 2017. That in Volta we have 5,000 stream processor in total, and we have 80 SMs. And in each SM, we have 64 SIMD functional units per core, or 64 basically SP per core. Interesting thing that they added in NVIDIA Volta is that they added tensor cores specifically to support machine learning applications. So at some point, NVIDIA actually focused a lot on machine learning, and that's why they are now quite successful and they are making a lot of money. So they started adding some accelerator, even though GPU in general, the model is actually very good for machine learning, because in machine learning, you do a lot of matrix multiplication, matrix vector. But if you want to, that GPU is not enough for that. If you want to make much better, you need to design accelerators. And NVIDIA, for example, designed tensor cores for that specific operation for matrix multiplication in order to accelerate specifically that kind of operations that we have a lot in our machine learning. Tensor cores are still SIMD, MIMD. They are also sharing, but yeah.
Okay.
Yeah.
Okay.
So this is architecture of a V100, which we have 80 SMs, and you can see this L2 cache. I think we didn't have, for example, L2 cache in the first architecture that I showed you. You can check later, but. Okay, and these are some numbers about the performance, how much performance you can get. Like, for example, with single precision, you can get 15.7 teraflops, which is quite a lot. And if you use tensor cores for operation like deep learning, you can, for example, you can get 125 teraflops specifically for deep learning operation. And tensor cores are essentially optimized for doing this operation. So you have two matrices that they are in this architecture, they should be floating point 16, and then you multiply them and then you add them. Basically, you need to accumulate in order to do this multiply and accumulation. And then you have the result in 32 floating point. Yeah, and this is the same thing. Some people actually try to demystify the tensor core exact architecture that we have in NVIDIA. This paper is actually from Toromot's group. And they show, for example, that each warp, this is an architecture of tensor cores, microarchitecture in Volta. I'm not going into detail of that. You don't also need to know that for the interest of this course. But if you're interested to work on this topic, you can, of course, check this paper. So each warp utilizes 2 tensor cores. So meaning that each tensor core contains, basically each tensor core can work on 16 threads. So warp is 32 threads. So basically each warp works on 2 tensor cores. And each tensor core contains 2 octets, so-called octets, and 16 SIMD units per tensor core, meaning that 8 per octet. And we can do, for example, 4x4 matrix multiply and accumulate each cycle per tensor core. And if you look into it, basically the main functional unit that you have is these rectangles, and it's essentially this operation. you do multiplication, and then you have a reduction sum, a tree for reduction sum. Which is, why is that? Because you want to do dot product. It's essentially each of these elements, processing element is doing reduction dot product for you, and you can use it. It's also quite interesting here that unlike conventional SIMD, register contents are not private to each thread, but shared inside the warp, because that's needed when you want to do dot product. Otherwise, you have to repeat a lot of data, and you need to have many repeated data elements. But here you can actually load register values, and then you can share them a lot through these buffers. And essentially, they can work together to execute. But other companies also, they designed tensor cores. Like this one is from Google Edge Tensor Processing Units, but this actually coming from a little bit different paradigm, which is systolic arrays. And we're gonna also hopefully learn about systolic arrays later. But it's actually from one of our research we have done with Google on understanding Google Edge GPU. What are the shortcomings of them and how we can improve them, essentially. Okay. If you're interested about this work, you can check this one. And if you're want to learn about systolic array, you can watch this lecture. But probably we will also cover systolic array in later lectures. Okay, so after Volta, we have this Ampere. Nvidia A100 is one of the flagship basically GPU device back then. And so we have something 6,900 stream processor. We have 108 SMs and a lot of, and you can see 64 SIMD functional units per core. The interesting thing about NVIDIA N100 that I want to emphasize is support for sparsity. So these tensor cores that I showed, they are actually designed for dense matrix multiplication. And people have said that, okay, for many of these machine learning, we specify, in order to be more efficient, we don't need to do a lot of operations. So we prune the network and we have a lot of sparsity in our matrices. And if you run them, you can see that the performance of Volta is not good. So in this work, in this generation Ampere, they try to provide better support for sparsity. Once your matrix is a bit sparse, you can still get better performance. But I'm going to show a number which you can see that it's not that great. So for deep learning, if you have dense matrix, this is the 312 teraflops that you can get. But if you have some sparsity, you can just get the double of that, But in many works, they actually show that we have 90% sparse values, or 95 or 99. So you really, for example, if you have 90% sparse, you really want to have, I'm losing my voice, by the way. You need, for example, 10 times the speed up, right? Because you have, but because of irregularity and also many other reasons, they cannot get that much performance improvement. But still, they are trying to do better when they are sparse. And here is the architecture that they have for basically tensor cores. Later on in 2022, we have Hooper architecture that has 144 SMs on the full architecture and 60 megabyte of L2 cache. Interesting point about this architecture is that they added a lot of different, basically, precision for data. Why is that? Because they realized that for many of these machine learning training, for example, we don't need 16-bit, 32-bit, 64-bit data. So we can do operation on 8-bit data. And that can provide a lot of efficiency. And also you can reduce how much you're getting, how much you're consuming memory bandwidths for that. We are on time. Yeah, so yeah, this is what I want to basically underscore here, that they added different precision to their design. And this is the most recent one, NVIDIA Blackwell, that they announced it last year. I'm not sure if it's already released. I think maybe some of them in GeForce, because NVIDIA has different category. There are some GPUs that they are coming from for graphics. I mean, you can still use those GPUs for doing computation as well. You may know it like 3080 Ti, I don't know, 4090 something. So you can use them for game, of course, but you can also use them for doing high performance computing. I think some of them they already released, but I'm not fully sure. But this is, for example, one of the architecture that they announced that they call it, I guess, super chip, that they have two Blackwell chip, which I believe they are B200 version, and also a CPU chip that they have it on this, and this is quite powerful. And they can combine these super chip in a cluster and make a super computing out of it. So this is a picture of this NVIDIA Blackwell architecture. I don't think this one is for B200. It's actually it's very hard to find the picture for now because it's not already released that much, and there are a lot of marketing information. That's very hard to filter marketing information and get the information that you can rely. It's not that easy, but is one of the architecture of Blackwell. So in B200, which I think is the most powerful chip of this architecture, they have 160 SMs or 160 cores, and they have 8 TB per second memory, which HBM3, and you can have up to 192 GB of data. And you can see that the performance they get for example, 32 floating point is 180, and for 64 floating point is 90 teraflops. Is it exciting? Yeah. Is it even more exciting if you know the history? That people around 2000, so they were trying to see how they can make a supercomputer of 1 teraflops. And then very soon, actually, NVIDIA, comes with this architecture, and then we have teraflops in our pocket nowadays.
Between the last couple graphics cards, it just looks like the image, they just grew the amount of like.
This is die. No, this is only the die. This is the die of GPU or the chip.
But all they've done is just added more.
Yeah, exactly. The fundamentals are the same, but yeah, but they're also adding some accelerator like tensor cores, as we discussed, and also support for lower precision. I believe in Blackwell, they also provide support for 4-bit data, 4-bit precision. So yeah, these are the changes that they are making. They are not fundamental in my opinion, but they are doing, I think they are doing their way to keep up with the performance. But there might be fundamental different way to do computation, of course, which we're gonna also see later lectures. For example, with memory-centric computing, storage-centric computing, you may not need to have that many GPUs to do computation. We already actually, this last week, when we were in Ask Plus, we presented 2 papers related to that you can do a large language model by using memory-centric computing and get the better performance, which if you want to get that performance, you need to combine many GPUs to get that. So that shows maybe we need to rethink about if what we are doing is a good thing or not. Okay, so I'm showing you these pictures again because I want to share some takeaway with you that essentially each GPU is quite powerful and it's getting powerful and powerful, but then today's applications they need a lot of memory capacity, and at the same time they need a lot of computation power. So people combine many GPUs, several GPUs in a cluster to basically provide collectively higher memory capacity and higher computation power. And that's why the interconnection network is going to be fundamental problem as we go also in the future. It was very fundamental and hard problem to solve in the past, but it's also getting harder and harder.
Is the demand outpacing what we can design?
I couldn't follow the question.
So is the demand for like AI processing such as that outperforming the actual demand we can?
Well, it also depends. So I would say that it also depends on the models. So as you make your models also more intelligent, you may not need to be also that huge, which actually we have seen recently that by making some model more optimized, you don't need to, for example, have that sophisticated hardware to run it. Yeah, general trend is that people just train more and then make the model bigger and bigger. Yeah, exactly. But I think that's also going to be one of the important research problem as we also go to the future, how we can make our models much smarter and less compute hungry, because maybe you don't need that, because our brain, I don't think is that power hungry. Okay. And these are some interconnection network that people propose in Nvidia in different generation to combine. So this architecture, they provide all-to-all connection among NVLink domain of 72 GPUs, which actually for Blackwell. So they combine 72 Blackwell GPUs in this cluster using this interconnection network, essentially. Okay, so there are some food for thought. So we haven't covered systolic arrays, but we're gonna hopefully cover it. But there is also a lecture that you can check if you are interested. But essentially, there are some questions that which one is better for machine learning, because there are companies that they are using systolic arrays like Google TPU, for example, and the GPU that they are still GPU, more GPU to be that systolic array. So which one is better for machine learning? Which one is better for image vision processing? Which type of parallelism each one exploit, and what are the trade-offs? If you're interested in such questions and more, I would recommend that you take this course. Some of you, I know you already, you're already taking this course. But yeah, if you're interested, you can take this seminar in computer architecture course and our master level course for computer architecture that we go into cutting edge research more deeply. To learn more about GPUs, I would recommend these courses again. And with that, I will conclude today's. No question, I guess, right?